In this video, we will explore the connection between the time-reversible nature of quantum systems and the irreversible increase in entropy at the macroscopic level. This investigation takes us to the heart of the tension between the quantum world, where time appears to be reversible, and the macroscopic world, where time moves irreversibly forward. In the quantum world, the Schrödinger equation governs the evolution of quantum states. This equation is time-reversible, meaning that if you know the wave function of a system at once, you can run the equations forward or backward in time and predict its behavior in either direction. As in classical mechanics, the laws of quantum mechanics do not distinguish between the past and the future. Time can theoretically flow in either direction. For example, if you take the quantum state of a particle today and evolve it backward in time, you will end up with a quantum state that behaves just as well as it does when evolving forward. This time, symmetry is the basis of quantum mechanics. At the quantum level, systems governed by the Schrödinger equation evolve deterministically and symmetrically in time. If we know the initial wave function of a system, we can evolve that system both forward and backward in time with perfect accuracy. This time reversibility is deeply embedded in quantum mechanics. If you rewind an isolated quantum particle, it will return to its previous state without any problems. This time symmetry shows that the quantum world does not prefer an intrinsic direction for time. Theoretically, if we had perfect knowledge of a system, we could reverse the system's evolution as easily as we could run it forward. This is true for isolated quantum systems that do not interact with the outside world. However, in the macroscopic world, time flows irreversibly forward. This is based on the second law of thermodynamics, which states that the entropy of a closed system tends to increase with time. Entropy is a measure of the disorder of a system, or the possible ways it can express itself in different orders. Systems evolve toward a state with higher entropy, which is statistically more likely. At the macroscopic level, we observe the second law of thermodynamics. Entropy increases over time, leading to an irreversible arrow of time. Whether we watch a cup of coffee cooling, ice melting, or galaxies moving apart, we see the same direction. A progression from lower to higher entropy. This contrasts sharply with the quantum level, where time evolves symmetrically. While this may seem like a contradiction between time reversibility in the quantum world and macroscopic irreversibility, the two views complement each other. The time-symmetric structure of quantum mechanics sets the stage for the irreversible increase in entropy that we observe at the macroscopic level. Micro-level symmetry in the quantum world gives rise to the one-way flow of time in macroscopic, large-scale events, i.e., the arrow of time. The answer lies in a phenomenon known as quantum decoherence. Decoherence occurs when a quantum system, when interacting with its environment, moves from a state in which it can exhibit quantum superposition and interference to a state that behaves classically. This is a kind of blurring of quantum states due to environmental interactions that are, critically, irreversible. For example, imagine you have a quantum particle that behaves like a fine wave, existing in a superposition of states, both here and there at the same time. If this particle remains isolated, it retains its quantum behavior and its evolution remains reversible with time. However, as soon as this particle interacts with its environment, for example, when it hits an air molecule, its quantum state becomes entangled with the environment. The decoherence process causes this fine wave to collapse into a classical, well-defined state that is irreversible on a macroscopic scale. In essence, decoherence prevents us from seeing the full quantum time symmetry of the macroscopic world. When the system interacts with its environment, the information about the quantum superposition is scattered and becomes inaccessible, effectively leading to a loss of coherence. From that point on, the system appears to evolve irreversibly as the entropy of the entire system, including the environment, increases. This interaction with the environment is key to understanding how quantum systems that are theoretically time-reversible give rise to macroscopic irreversibility. This process is irreversible. When a quantum system decoheres, it cannot spontaneously reassemble in a way that would allow time reversibility. In a sense, the system has become part of the macroscopic world, and its behavior now obeys the laws of thermodynamics, including increasing entropy. The beauty of this reconciliation lies in the fact that macroscopic irreversibility emerges from the statistical behavior of many quantum systems. Every particle or quantum component evolves according to time-reversible laws, but when you consider the collective behavior of a large number of particles, the overwhelming majority of possible future states are those with higher entropy. Here's an analogy. Imagine you have a deck of cards carefully sorted from ace to king. You shuffle the deck randomly, similar to letting a system evolve. The vast majority of the arrangements are disordered, high entropy, and only one is ordered, low entropy. Statistically, after shuffling, the deck is almost certain to be in a higher entropy state. Although there is nothing in the laws of physics that prevents the cards from being perfectly ordered again after shuffling, the chances of this happening are so astronomically small that it is practically impossible. Therefore, while the laws of quantum mechanics remain time-symmetric, the emergence of macroscopic irreversibility is a consequence of probability. In the evolution of complex systems, every quantum process, even if it remains reversible, leads to a statistical increase in entropy. In quantum mechanics, we can also talk about entropy, specifically von Neumann entropy, which measures the amount of uncertainty or disorder in a quantum system. As quantum systems become more intertwined with their environment during decoherence, their von Neumann entropy increases. This means that as the system interacts with its environment, information about the initial quantum state is lost to the outside observer, effectively leading to an increase in entropy. This is where time asymmetric behavior comes into play, as when a quantum system becomes intertwined with its environment, the process of uncohering it, or reversing decoherence, becomes extremely difficult, as the information is distributed over countless degrees of freedom. In practice, this makes reversing such interactions nearly impossible, and is consistent with the irreversibility we observe at the macroscopic level. Although quantum systems are theoretically reversible in time, in practice, reversing the effects of decoherence and entanglement seems unlikely, like reversing the mixing of milk into coffee. This irreversibility is at the core of our perception of the direction of time. Although quantum mechanics suggests that the universe can, in principle, flow backward, our macroscopic experiences and observations, where we see broken glasses stay broken and stars age, are governed by the statistical irreversibility of large-scale systems. The irreversible increase in entropy resulting from quantum decoherence ultimately defines the arrow of time that we experience. While individual particles follow time-reversible equations, the collective behavior of many particles leads to the resulting irreversibility that we observe, giving rise to the arrow of time. At this point, I leave you with a provocative question. If we could completely isolate a complex quantum system from its environment, could we reverse its evolution and witness the backward arrow of time? Or is such isolation merely a utopia in our entropic universe? First, let's consider what would happen if we isolated a quantum system. In such a scenario, the system would be completely governed by the Schrödinger equation, which is time-reversible as we know it. In principle, if you knew the state, wave function of every particle perfectly and isolated it from all external influences, you could evolve the system forward or backward in time without any problems. In theory, by exactly reversing all quantum states, like reversing the speed of every particle in a classical system, the system would evolve backward in time, undoing previous interactions and retracing its steps to an earlier state with lower entropy. This would essentially be a time-reversed trajectory, a true rewind of the system's evolution. While this is theoretically possible, the real challenge is to achieve perfect isolation and perfect knowledge of the system's quantum state. For any complex quantum system with many interacting particles, such as a molecule, atom, or larger system, isolating it from its environment becomes exponentially more difficult. Every interaction, whether it's the cosmic microwave background radiation, stray photons, or even the faintest vibration, leads to quantum decoherence. When decoherence occurs, the system becomes intertwined with its environment, and the clean reversibility of quantum mechanics is lost on a macroscopic scale. In a larger system, where you're dealing with billions or trillions of particles, the odds of maintaining perfect isolation drop dramatically. Even the slightest perturbations can quickly propagate through the system, causing irreversible macroscopic changes. In practice, these systems inevitably exchange energy with their environment, making isolation difficult and irreversibility inevitable. As soon as any interaction occurs, entropy begins to increase, and we lose the ability to reverse the evolution of the system. Another obstacle is the problem of quantum measurement. As soon as we try to observe or measure the quantum state of a system, we somehow disturb it. Any interaction that extracts information from the system, whether it is a measurement or a slight environmental interaction, collapses the wave function and introduces irreversible changes that make the system no longer perfectly isolated or reversible. This is directly related to the observer effect in quantum mechanics, where the act of measuring affects the system. Our universe is a thermodynamic system governed by the Second Law of Thermodynamics, which pushes the arrow of time forward through a continuous increase in entropy. The early universe began in a low entropy state, and since then the entropy has been increasing as systems interact, intertwine, and exchange energy. The fact that we live in such a universe where entropy is always increasing places practical limitations on achieving perfect isolation. Even if we could isolate a quantum system perfectly for a brief moment, the fabric of our entropic universe would work against maintaining such isolation indefinitely. Eventually, some environmental influence will intervene, disrupting the isolation of the system and pushing it forward along the arrow of time. Therefore, while reversing time may be possible in small-scale, highly controlled quantum systems, e.g., in laboratories with individual particles, macroscopic reversal of time, a full-scale backward arrow, remains a pipe dream according to current physics. Interestingly, experiments with quantum systems, for example with a few particles or small molecules, have shown effects similar to reversing time. In controlled environments, scientists can manipulate quantum states and perform quantum reversals, where the system appears to partially reverse its evolution. However, these reversals are extremely short-lived and limited in scale. The larger and more complex the system, the more difficult it becomes to reverse the arrow of time. For example, certain systems of quantum computers can reverse errors through quantum error correction. But this is very different from reversing the entire thermodynamic process. Even these systems eventually succumb to entropy as interactions with the environment accumulate. In the large entropic universe we live in, perfectly isolating a complex quantum system to observe the backward arrow of time is, for all practical purposes, a fantasy. In classical thermodynamics, time asymmetry is related to the second law of thermodynamics, which states that entropy tends to increase in isolated systems. This creates the macroscopic arrow of time. Events such as a broken egg not spontaneously recombining or gases not expanding and returning to their original state are examples of this. However, at the quantum level, things are different. In quantum mechanics, the fundamental equations, such as the Schrödinger equation, are symmetric concerning time. Even if you reverse the direction of time, the evolution of a quantum system remains consistent with these equations. The evolution of an isolated quantum system makes no natural distinction between the past and the future. That is, these systems can be reversed and return to their initial state. This is why it may seem that entropy does not increase in a closed, idealized quantum system. However, in quantum systems, entropy is measured by the von Neumann entropy. This entropy remains constant in closed systems because there is no loss or gain of information. However, when a quantum system interacts with its environment, for example through quantum decoherence, entropy increases, as in classical thermodynamics. Interaction with the environment leaks the system's information into the environment, leading to macroscopic irreversibility. The quantum measurement process is of particular importance in terms of time as symmetry. Before the measurement, the system exists in a superposition of probabilities. However, when a measurement is made, this superposition collapses into a single state. This collapse of the wave function is irreversible and introduces a kind of time asymmetry into the quantum system. Although the system continues to evolve with symmetric equations concerning time after the measurement, the act of measurement has created an irreversible change, which gives rise to the era of macroscopic time. Quantum decoherence is a similar irreversible process. When a quantum system interacts with its environment, the system's information is transferred to the environment, forcing the system into a classical state. This process mimics the collapse of the wave function and results in an increase in entropy. As a result, time asymmetry and entropy increase in quantum systems arise through measurement and environmental interactions, while isolated quantum systems exhibit symmetric evolution concerning time. Measurement and decoherence allow irreversible processes to occur in the macroscopic world. Can time flow backward in quantum systems? Theoretically, if we could completely isolate a system and achieve perfect control, we could reverse its evolution and return the system to its original state. However, in practice, environmental interactions and measurements allow irreversibility to seep into the quantum world, causing systems to conform to the macroscopic arrow of time. As a result, time asymmetry and entropy increase in the quantum world arise through interaction with the environment and measurement processes. This brings quantum dynamics into harmony with the macroscopic world. Thanks for listening, and take care.